Yo, what's going on guys, Tanmay here for Simple Snippets and welcome back to another video tutorial on data structures and algorithms. And as the title of the video suggests, today we're going to understand the working of searching operation in binary search tree and we are going to use the recursive approach. Now before we proceed, in case if you have missed any of the previous tutorials from this DSA course, from this DSA playlist, we've been talking about binary trees and binary search trees and we started with the implementation of binary search tree. When I say implementation, I mean writing of code to implement all the binary search tree operations. We've discussed what is a binary search tree, we've discussed the concept of tree data structure and everything is covered. So do check out this playlist. I'll drop the link in the video description. And for all those who followed me throughout this DSA course, in the last tutorial we discussed iterative search. So it is also a searching technique, but instead of using recursion, we used iteration instead of recursion, which means we used loops like while loop. So if you have missed that video as well, do check it out. In this tutorial, we are going to use the concept of recursion. So we are going to use recursive functions. If you don't know what is recursive functions, I have a separate dedicated video on what is recursion and how recursive functions work. Do check that out. It is kind of confusing as a beginner. So I'll link that video also. You can see a card. And now that the introduction is done, let's proceed with today's tutorial. If you're new to my channel, my name is Tanmay Sakpal and I do a lot of computer science and information technology video tutorials like computer programming, development, technology talks and a lot more on this channel. So if that's something you're interested into, then definitely subscribe and turn on the notifications to get the latest updates and never miss out on such important topics. So on the right hand side, this is our binary search tree. This is the root node n1 which is created at an address of #31 and this is the value which is the center position or center element in this node. So this pink structure is the node structure. The left and right elements are nothing but pointers which store the address of the left and right child respectively. These addresses are not real, they are fake addresses, they are just for representation purpose. And this is a binary search tree and not a regular binary tree. And the only difference being that in a binary search tree, for a particular node, for example, let's say for this node n1, all the values in the left subtree, that is 18, 10 and 25 are going to be less than that node value which is 30, and all the values in the right subtree which is 45 and 65 are greater than the value of that node. And this principle is followed throughout all the different nodes, and that's the only difference, but we've already discussed all this, so I'm not going to waste time over here. And our goal today is to perform searching operation. When I say search, we are looking for a particular value in this binary search tree. Let's say you want to search for 45 or 65 or 25. So how do you search that? Now we've already talked about the iterative search as I mentioned using the while loop. Today we are going to discuss recursive search by using recursive functions. And we are first going to take a look at the pseudocode which is over here. You can see we're going to dry run this pseudocode onto our example and then proceed on to the dev C++ ID and convert this pseudocode into our C++ program and continue with the implementation of binary search tree which we've been doing throughout the last few tutorials. That is the implementation of binary search tree and all its operations. Okay, so let's assume that we want to search for the value 25. Okay, so you can see 25 is over here. How do you reach over here using this recursive search function? This is the root node. Traversal always starts from the root node. So in order to find 25, we will have to traverse this entire tree, correct? And to do that programmatically, we need to understand how the step-by-step process works, which this pseudocode will give us a good idea about. So starting off with this recursive search, so this is the function name recursive search. It has a return type of tree node star, which means that it will return the address of a particular node when you find that particular value, or it will return null depending upon whether there is a value of 25 or not. In case if the value doesn't exist, it will return null, and we'll see that in the pseudocode. There are two arguments that are passed in this recursive search function. First argument is the current tree node address. So tree node star r is nothing but a pointer which will point to the current tree node, because recursively we will traverse the tree, right? So every time the current node value will change and that will be pointed by this r pointer. And the reason why I'm saying pointer is because in C++ we are going to use the concept of pointers to traverse the entire tree. And the second argument is nothing but the value that we are searching for. Okay, so this is going to be fixed. It is going to be 25 as I mentioned. And now let's go inside this function. We have three simple if else conditions. the first condition states that if r equals to null, or if r dot value equals to the value that we are looking for, then in 1.1 just return r. So this condition, that is the first step, will only be true when you find the correct match or you don't find match at all. Okay, so let's start with the execution. Right now we're looking for 25, right? So this value is 25, and when you start with the execution, let's do the first recursive search call. This will be the first recursive search call. You will start from the root node, so you'll pass n1. So r is going to be n1, and value, that is val, is of course going to be constant. Let's write val over here. I'll write val equals to 25. It is constant, correct? So again, r is equal to n1 in this case, and this val is 25. So first step, we check if r equals to null. We just said r is pointing to n1, correct? R is equal to n1, that is r is storing the address of n1. R is a pointer. So r is not null, obviously. So this statement becomes false. Now there is a or in between, so even this condition needs to be checked. And over here we are saying or r dot value equals to val. So what is r dot value? R is currently pointing to n1. What is the value inside n1? It is 30. Now this is also called as data or key. We are calling it value. So r dot value is nothing but n dot value, which is 30. Is it equal to the value that you are looking for? We are looking for 25. Is 30 equal to 25? No. So of course the first statement, that is the first if block, both these conditions have become false. So this if block will not be executed, and we will go to second else if block. Okay. So far so good. Now over here in the else if, we are checking if val is less than r dot value. Val that we are looking for is 25. Is 25 less than r dot value? R is pointing to n1. N1's value is 30. Is 25 less than 30? Yes. So now this statement has become true. So this else if block will be executed, and we will execute 2.1. Now in 2.1, you can see that we are calling recursive search again. So now this is a recursive call, which means that this recursive search is calling recursive search again. And this time we are saying r of left as the first argument and int val, which is again the same value as the second argument. So this value int val is going to be 25 only, but r dot left. So r, as I mentioned, is currently pointing to n1. When I say r dot left, it means n1's left. What is there to the left of n1? As the left child, it is hash 16, which is nothing but the address of n2. So basically over here we are passing n2. Okay. So we are giving a recursive call and calling recursive search again, but this time we are passing a new node, which is n2. So you are traversing from n1 to n2, and now the first recursive search function has given a recursive call to this second recursive search, and we've passed n2 at this step 2. So when this happens, the first recursive call will go in a pause state at this step 2. Okay. So I'll write pause state over here and denote the step at which it got paused, correct? And now we can begin executing with the second recursive search function. Now you can see we are on the correct path, because from n1 we traverse to n2. We have to still reach to n5, right? Because n5 is having the value 25. So now we can again start with the execution of this recursive search pseudocode for the second call. For the second call, r is nothing but n2. So r equals to n2, and this val of course is 25 only. Again you will check if r equals to null or r dot value equals to val. R is not null because r is n2. So first condition becomes false. Then we have a or clause, and then we say r dot value. Now r this time, as I mentioned, is pointing to n2. n2's value is 18. So r dot value is 18. Is it equal to val? What is val? Val is 25. So this is also not equal. So even this condition becomes false. So first if block is not executed, you will move to second if block. Over here you are checking if val, we just said val is 25, we are looking for 25. Is val less than r dot value? R dot value we just said is 18. Is 25 less than 18? No. So even second step will not be executed. You will move to step 3, which is else block, and now else block will be executed because the first two blocks did not get executed. So obviously we are now remained with the else block, and when the if and else if doesn't execute, the else block will always execute. There is no condition check. So now we will say 3.1, and this is a recursive call again, but this time we are saying r.write. So r, as I mentioned, is currently pointing to n2. What is there to the right of n2? It is hash 26. Hash 26 is the address of n5. So over here we are passing n5, and this val value is passed as it is, so it is 25 only. So now we have a third function call from this second recursive search, you can see over here, and this time we are passing n5 and the same value 25 that we are looking for. So of course when this happens, this second recursive call will again go in a pause state, and it got paused at step 3.1. So let's write 3.1 over here. The reason why I'm writing this pause state is because after executing the last recursive call, it will come back to the calling function. So we have to keep a track at where exactly it got paused. Okay. And now we can begin with the execution of the third recursive search function. Now at this step, r is equal to n5 and the value is of course 25. So at the first step over here, we check if r equals to null. R is not null, r is equal to n5. So this is false. But the second condition over here, you can see r dot value. R is currently pointing to n5. n5's value is 25. So is 25 equal to val? Yes, because val is 25. So now since one of the condition in the if block is true and there is a or in between, this entire if block becomes true, and we go inside this and we execute step number 1.1. We say then return r. So we simply return r. R is nothing but n5, that is the pointer pointing to n5. So now that will be returned to the calling function. So this r is returned from this recursive search function back to the calling function. Who called the third recursive search? It was the second recursive search. So now this will come back over here. The second recursive search will resume its operation from step number 3.1, and there is nothing more to execute after 3.1. So even this recursive search will return back to the first recursive search. Now first recursive search will resume its operation after step 2. Step 2 is done. So for first recursive search, the step 2 part is done. And when this step 2 part is done, of course step 3 will not be executed, because only one block, that is either step 1, which is the if, or else if, or else will be executed. And since the else if was executed, this recursive search will also complete its execution and return back to the calling function, which will be the main function when it comes to C++ programming. And that is how you'll get this n5's address returned back. And when you get that, in the main function, you can make a check whether you've got null value or you've got an address of particular node. And if you get an address, then you can say that we found the value. But if you get null, you can say that we did not get any value. Now when will you return null? Let's say you are searching for some random value 77. In that case, you will recursively traverse from n1 to n3, n3 to n6. And lastly, the r will start pointing to null, and that will be returned. Now if you're still confused, what you can do is you can pause the screen, take the value as 77 or any random value which is not there in the binary search tree, and again follow this step-by-step process by dry running this recursive search, and then you'll easily understand when you get the null value. Okay, so this was the pseudocode and working of recursive search operation in a binary search tree. Now let's convert this pseudocode into regular C++ code and try to run this and see if our program is working fine. Okay, so as you can see on the screen, I have opened up my Dev C++ IDE, and you can see quite a lot of code already written. That is because we've been implementing the binary search tree operations from many previous tutorials, and we have been taking one operation at a time. So this is our custom BST class, inside which we've written all the different binary search tree operations like insertion. Then we have printing, that is traversal. We've done the pre-order, in-order and post-order traversal also. We also did the iterative search, and if you scroll below, this is where we will write the function for recursive search. And this is all inside the binary search tree, that is BST class. If you scroll down in the main function, we've created the object of BST class, and we've created a menu driven program. So depending upon the option selected by the user, we will perform that appropriate BST operation. So for example, if the user enters 1, we will insert the node. If the user enters 2, we will perform the search. This is the topic today. If the user enters 3, we will do the deletion. If the user enters 4, we will do the printing. Now I have already briefed all the details about this menu driven program in previous tutorials, so I'm not gonna go into the details. But in the switch case, in the case 2, this is where we'll perform the search. This was the iterative search. I'm gonna comment it out, and below this just copy this, and this is where we'll do the recursive search. I'll explain to you what this is. Let's first type the recursive search function in the BST class. Okay, so you can see I've already copy pasted the entire recursive search code. You can pause the screen and type the code yourself. I highly recommend that you type the code at least once if you're a beginner. But don't worry, I'm gonna be sharing this code with you guys, and you can check the link in the video description to our official website where I've shared the article, and it has the full code, so you can go and check it out over there. But you can see this and compare it with the pseudocode which I have shown on the right hand side. This is the function prototype. We are passing tree node star r as the pointer and the value that we want to search. This is step 1, that is the if condition, if r equals to null, or, so this is how you write or in C++, and we are saying r of value equals to val. Now if you are wondering what is this sign, that is hyphen and angular bracket, it is because r is a pointer which is pointing to the object, and the object is of tree node type. So in order to access the value of that object using this pointer, you have to use this syntax. If this was a regular object and not a pointer, you would have used the dot operator. But since it is a pointer, you have to use this syntax. So you have to use the pointer to object syntax in C++. So when either of these conditions are true, you say return r. Else, if the value is less than the r of value, you have to recursively search through the left subtree. So you say r of left and you pass the value. And if the value is greater, so if it is not equal and if it is not less, obviously it is going to be greater. So that's why we have directly else, we say recursively search the right subtree. Okay, so makes sense? Pretty easy. Let's save this. Let's scroll down to the main function. In the main function, as I mentioned, we've created the BST object. This object will now be used to call that recursive function. In the menu driven program, we are creating a tree node pointer to the object by using this syntax. So when you say tree node star new node equals to new tree node, an object is created in the heap memory of tree node type, and this new node is nothing but a pointer which is pointing to that object. I've explained this concept in previous tutorials, so if you followed this DSA course, you should be able to understand this. And in the switch case, what we are doing over here, simply change this obj.iterative search to obj.recursive search, and you have to pass the root node. So you say obj.root, comma, the value that you're taking from the user. So what is this obj.root? So obj, as I mentioned, is an object of BST class. Now if you scroll to the top in the BST class, you can see we've created a data member which is a pointer of type tree node, and its name is root, and it is in the public section. So that's why you can directly access obj.root. So the recursive search function needs two arguments. The first is going to be a pointer of type tree node, that is what we are passing. So we'll start with the recursion starting from the root node, right? So that's why we say obj.root. And the second thing is this val which we are taking from the user. You can see we say search and we say enter value of tree node to search in the binary search tree, and we say cin val. So this val is nothing but a variable that we create on the top. You can see over here in the int main function, we take it from the user and we pass it in this recursive search function. Now you can see this recursive search function is on the right hand side of the equal to sign, and on the left hand side we have this new node pointer which will store the address of the node when you find that particular node which has the same value that we are looking for, or it will store null if you don't find the value. So this new node, as I mentioned, is a pointer which points to our object in the memory, and it will then start pointing to this new node or the node that we find in the binary search tree. So that's why it is on the left hand side. So it will store the address because this recursive search will return a pointer, hence the return type is tree node star. Okay, makes sense? Alright, so now let's try to run this code. Let's see if this works. Go to compile and run. Okay, so things are working fine. Let's try to create the same tree that we did the debugging on. So this is our tree. The first thing we have to do is we have to insert these nodes. We've already implemented the insertion operation previously, so you can check that out if you've missed it. I'm gonna hit option 1 and enter 30, which is the root node. You can see value inserted as the root node. Again, option 1, let's insert 18, which is the left child, value inserted to the left. Again, option 1, let's insert 45, value inserted to the right. Option 1, hit 10. Option 1, then we have 25. Option 1, we have 65. Let's clear the screen. Option 5. And now let's print the tree first. So option 4 is printing. We've already done with the printing. So you can see in a 2D way, the tree is printed and it is kind of rotated in anti-clockwise direction in 90 degree. So 30 is the root node. Then we have 18 and 45 as its children. For 18, we have 10 and 25 as the children. And for 45, we only have a right child, which is 65. So now we want to search for a particular value. Let's search for 25. So for that, first we'll have to enter option 2. So you can see search, and now it is asking the value of the tree node you want to search for. Let's hit 25 and let's see if we get the answer. When I hit enter, you can see we are getting value found. Now if you go to the code, after you call the recursive search, you simply have to check if this new node value is not null, then you can say value found. And in the else block, when the new node will have null value, you can say value not found. Okay, so this check is supposed to be made on the coding side in the main function. Now coming back to the code again, let's enter some random value as 77. Again, let me first clear the screen. Let's print the tree. Now let's go to the search option, option 2. And now let's enter 77. We don't have 77 in the tree, so we should get value not found. When I hit enter, you can see I'm getting answer as value not found. So this means our program is working fine. Our recursive search is working perfectly fine. And we've successfully implemented the recursive search operation in binary search tree. Okay, so I'm gonna wrap this video over here. I hope you understood how you can use recursion when you are implementing search operation in binary search tree. Do note that searching in binary search tree is different from searching in a regular binary tree, because binary search tree has this extra benefit, extra principle, where the values are arranged in particular order in such a way that for a particular node, all the values in the left subtree are lesser than that node value, and all the values in the right subtree are larger than that particular node value. Okay, so that's why in binary search tree the searching is very fast, and we've discussed the time complexities and compared it with linear search also in previous tutorials, so do make sure to watch that. That is important to understand. And I hope the practical side is now clear. We dry run the pseudocode, we converted it into C++ code. So if you've understood, if you like this video, please give it a thumbs up. Let me know in the comments how this video was. Do share it with your friends. Definitely subscribe onto our channel for more updates on programming tutorials and a lot more. And I'll see you guys in the next one. Peace.